All right, let's take a look at the worksheet for Chapter 6, Section 3. Okay, start with the multiple choice questions. Again, I'm not just going to look for the correct answer. I'm also going to look to be able to explain why the other three responses are incorrect. The notation for sodium chloride stands for 1. Now we have crystal. That's not going to be the case because we know that ionic solids, they do form crystalline structures, okay, lattice structures, but in terms of 1 sodium and 1 chloride ion, that's not enough to make a crystal. Okay. We also see that there is 1 sodium atom and then 1 chlorine atom. They're both ionized, so standing for 1 atom. That's obviously not the case because there are 2 right there. Now, when we get into a little bit of a word game here, we see that molecules are associated with covalent bonds. And so this is not a covalent bond. This is an ionic bond. So I'm also going to rule out B. It's not a molecule. It's considered an ionic compound is the word we use or the term we use. So I'm left with formula unit. And in fact, this is a formula unit for sodium chloride. It's the smallest unit for that ionic compound that maintains all of its chemical properties. Number 2, in a crystal of an ionic compound, again, you call these ionic compounds, not molecules. In a crystal of an ionic compound, each cation is surrounded by a number of, surrounded by a number of molecules? No, we're talking about ionic compounds, okay, so it's not molecules. The question says each cation is surrounded by a number of, so it can't be positive ion. The reason I know that because cations are positively charged. And so if they were surrounded by positively charged ions, they would repel each other, and that compound, that crystal, would just explode. Okay, it would just shatter. So it can't be a positive ion. Dipoles, surrounded by a number of dipoles. Again, a dipole is 2 poles. Di referring to 2, poles referring to polarity, having 2 different partial charges on either end. Again, there's going to be a negative, a partially negative end, partially positive end. And if you have that partially positive end next to a cation, boom, you got repulsion. That thing's going to shatter. So again, I'm left with a negative ion. This is correct. This is the source of attraction. You have a positively charged cation attracted to negative ions, and they are that's how you create a crystalline structure. You surround positives with negatives. You surround negatives with positives. Moving on to number 3. Compared with the neutral atoms involved in the formation of an ionic compound, the crystal lattice structure that results is, now again, I've said this a lot. Nature favors low energy arrangements. Low energy arrangements are supported or favored by nature. So, the crystal lattice that results is, so what nature has done, okay, this is the result. We had some sort of arrangement. Nature has done something to it. It's arranged these different ions in this crystalline structure. And so the result, going to be higher in potential energy? No. Nature favors low energy. So nature wouldn't create a high potential energy situation. Equal in potential energy, well, why would nature make this change happen if there was no increase in stability? Okay, and similarly, the result is unstable. That's the same thing as saying high potential energy. Again, nature doesn't favor unstable arrangements. It doesn't favor high potential energy arrangement. It favors low potential energy arrangements. So that'd be B. Number 4. The lattice energy of compound A is greater in magnitude than that of compound B. What can be concluded from this fact? So lattice energy, remember the definition of lattice energy, the amount of energy that has to be put into an ionic compound, a sample of it to break the bonds of 1 mole of that substance. So lattice energy is greater for A. That means more energy has to be put into compound A to break all those bonds, to overcome those positive negative attractions. B, it takes less energy to do that. Yeah, remember lattice energy is also used as a representation of bond strength, so let's look at these options. Compound A is not an ionic compound. Well, that's probably not going to be true, because what we should be learning from the reading is that ionic solids, ionic crystals, have some of the strongest bonds that we see in nature, and so having a high lattice energy is consistent with being an ionic solid, so that's not something that we would conclude. Compound A has larger crystals than compound B. That's not necessarily something that we're going to conclude. The size of the crystals has to do with the size of the ions, involved in making that crystal. Similarly, compound B has larger crystals. Again, the same way, we're not talking about the size of the crystals. We're talking about lattice energy. We're not talking about an individual bond either. Remember, lattice energy refers to specifically a mole of that substance. So we're breaking a lot of bonds, not just one, like we might talk about with bond energy that refers to covalent bonds. What we can conclude is that it will be more difficult to break the bonds in compound A than those in compound B. That's why the lattice energy is greater than A. It's stronger. These bonds are stronger in A than they are in B. And so it takes more energy to break those. So we will conclude B. Number 5, the forces of attraction between molecules in a molecular compound are generally equal to 0. Forces of attraction equal to 0, then there'd be no reason to bond. Okay, so that's kind of outlandish. I'm not going to go with that one. Approximately equal to the attractive forces among formula units in ionic bonding. Now, this might be not intuitive for you guys right now, but this is not true because we can conclude from the high melting points of ionic compounds that the attractive forces among the formula units in an ionic bonding situation are going to be very, very high. Okay? We have to add a lot of heat, okay, high melting point. We have to add a lot of heat, a lot of energy in order to break or overcome those attractive forces, especially when we compare them to a covalent bond. That's not nearly as much. So between molecules and molecular compounds, again, we're referring to covalent bonds there. Okay? Approximately equal to the attractive forces in formula units. That's not true. Attractive forces in ionic compounds are going to be a lot stronger. Weaker than the attractive forces among formula units. Well, that's actually what we just said. So I'm liking that one, but let's just double check that A isn't correct. Stronger than attractive forces. No. Attractive forces in covalent bonds are not going to be stronger than the attractive forces in ionic bonds. So we're going to go with B.